Você thanks Marcelo, Socorro, Jordana, Luan, and we fall to this meet, the first meet after the pandemic. I think your point. After, I think, CNPq, FAPEMIG, Departamento de Física e a UFLA, né? E now let's begin. In this work, we would like to study the anomalous low temperature behavior in one-dimensional Hubbard model, né? But standard Hubbard model in atomic limit. We choose this model because we are looking for some model in one-dimensional that have a pseudo-transition, only one dimension. In last year, almost found a pseudo-transition in Potts model, and the Hubbard model was the second candidate to our study anomalous behavior in low temperature. But first, it's important I talk about pseudo transition for us. In a long time ago, I think that the master degree of Jordana, you found some graphics with very high value of specific heat, very high. And in that moment, I look for this result, and we change the digit of the maple, and this very high value of specific heat disappear. We conclude that the problem was the numeric problem with maple. After Joseph visited us, and we working in model that have a high value of specific heat. No very high, but a high value is in specific heat in the region of low temperature. And Joseph explained to us that probably this value was associated to number of degenerations of eigenvalues of the Hamiltonian, and another thing he saw to us. But it was very important to us because in this moment we decide go back to model of Jordana work in this master degree, because in that moment our suspect that the problem isn't the numeric problem of the maple. After that, I will return and study the model with more detail. But in this sequence, I have an introduction, a standard Hubbard model, ground states, anomalous behavior, physical quantities, conclusion, perspective, and reference. So now I talk about the intuitive notion about anomalous behavior of pseudo transition. You use it to identify pseudo transition if you have mouse. If you have entropy graphs and you have a jump, fast growing of entropy, normally we associate this graph with one possibility to identify one pseudo transition. é que volta? Similar occur with internal energy, and we look for the specific heat. Normally, you have a sharp and fine peak. The same occur with susceptibility. But entropy is associated with first derivative, internal energy associated to with its first derivative, specific heat and susceptibility are associated with second derivative. But if we look for the correlation length, we have the same behavior, but we don't have derivative. What's important in this case is the distance between eigenvalues of the transfer matrix. Here, we don't have mathematical operation similar to the derivative, nothing this. Here, we have the distance between the biggest eigenvalue of transfer matrix to give us this very high peak in correlation length. This is very intuitive. But after the visit of Joseph, we return to model of work of Jordan, and we work hard in this model. And the interesting point of this model that the transfer matrix is 2 by 2. And if we consider double one near to 0, we can think that double 0 equal double 2. And in this condition, we can obtain the temperature of pseudo transition. This is the first step to obtain this pseudo transition using the model of the master degree of Jordan. In the same time, Oleg was visiting us, and we discussed these results with Oleg, and Oleg gave us another interpretation. Oleg looked for this shine and think about an effective easy model and map this model in one effective model. In this case, one easy effective model. And we put a magnetic field equal, effective magnetic field equal 0, the condition of the pseudo temperature appear. Today, Joseph used the same condition in the morning. This another, first we work Hamiltonian transfer matrix, we consider a process of perturbative process and we obtain our condition. Oleg look with this point of view, and we have the same results. In my opinion, very beautiful interpretation of Oleg to this problem. But here we was working with matrix 2 by 2, but after that, a good number of work about different kinds of spin model obtained pseudo temperature 2. But in last year, we returned to work in this problem, but in this time, we choose one nanowire. One nanowire, this nanowire, né? When you have 1, 2, 3, 4, 5, 6, spin one, and one spin half in the center of this nanowire. In this case, the transfer makes very big. With this nanowire, we change the dimension radically of transfer matrix. But in this problem, in this nanowire, we have another problem that we find with the Jordanian works, because here the maple and mathematics show us the power of precision. Where in this work it was necessary a big precision to obtain all quantities and all physics of this nanowire in near of pseudo transition. And another important thing that in this situation, the condition of pseudo transition, it's only one, as in first case. We use this three condition. Derivative of temperature, the lambda 3 over lambda 1, derivative of specific heat, and there's another identity we use it here. And in this model were necessary these three equations to obtain the pseudo transition. But in the same time, we return the diamond shine, but using Hubbard model. We change the spin model to Hubbard model. And in this case, we have in this dimmer, we permit the electron movement of electron, and we work with this model. And this model was important to us because it gives us an idea that the Hubbard model was important to study in only one dimension. This Hubbard model in diamond shine was a time model to us. But the next step was study the extended Hubbard model in one dimension. But the Hamiltonian is famous Hamiltonian, and this case is very interesting because there are a good number of articles that discuss this model. Benny Pincus, Mancini have a good number of articles. We have a good literature about this model. So for us, it's very important, these choice. And another important point, when you study the Mancini articles, we found these two pictures. If you look the picture of a specific heat, you see a peak you see a very high peak. If you see the figure of internal energy, you see a fast jump. Okay, in Mancini articles, they found pseudo transition similar that we was found in mass degree of Jordana, in this article of machine pseudo transition is here. But he don't speak more things about this. He showed this picture and they discussed some things. With it, we put our hands in the model, obtain the transfer matrix, the eigenvalues, normal, the algorithm, the normal algorithm to obtain the thermodynamics. And the second, the first step is plot the entropy or plot the ground state. In this case, we plot the entropy in temperature 0.01, and you choose magnetic field goes equal 0. And we plot the entropy, we can identify the possibility of pseudo transitions, simple looking for this field. And here we have these ground states. Inside we have the eigenvalues. The important is this region, these two regions are half filling. With this, we can study this model very near in this line. Here you have frustrates, and here you have an alternating pair of electrons. If you put magnetic field, these states, we have only spin up or only spin down. And here we plot the magnetization and entropy, in this case, using the half-filling band. With it, we look this line, and this line is associated still with transition. Now we have the ground states. You have the region where it's possible to find pseudo transition. Now we need to find. And in this case, we use these three equations that were important to nanowire. And we discovered that only necessary these two conditions. It's not necessary the another condition. It's not necessary this density. Here we plot the pseudo-critical temperature in function of magnetic field. Here we put V equal 0.54. Here you have V equals 0.56. Here we have V equals 0.58. V equals 0.54. It's exactly the half-fill band. And in this situation, the result of these three conditions is the same. When V equals 0.56, we have two conditions with same result, and another condition, we have a little difference. And we have V equals 0.58. We maintain two conditions equal and another difference, another with result different. Now, we can explore the thermodynamics of this model. Here we choose some magnetic field. We choose magnetic field equal 0.02, and with it we obtain the pseudo-critical temperature using this expression. And after obtaining the temperature pseudo-critical using this expression, we use it in another expression to obtain the second value of magnetic field. If these two magnetic field is very similar, okay, we have a good condition that this temperature is very well defined. And the same to another value of magnetic field. Here we choose V equal 0.56 to show the difference between the condition that we chose. Now we study the thermodynamic using this magnetic field and this temperature. Now, internal energy, here you have you can observe the jumping very fast and the jumping is slowly. Okay? If you return here, the jump very fast, the jumping very fast is associated to this region. The jump more slow associated to this region. Similar behavior you have with entropy, similar behavior you have with magnetization, and we have similar, the density is different. And now you use one temperature normalizer. Why? To put every curve in the same point. So we compare every curve in the same point. Então, you get the temperature and temperature pseudo-critic and use this temperature normalized to study these quantities. After you study the length, the correlation length, the specific heat, the susceptibility, and the compressibility. When we see here a fast growth, we see a sharp peak. Okay, it's exactly what we can see in this picture of specific heat in entropy. And here you have magnetization, similar we can observe in susceptibility. When You have a, a fast growing in magnetization. You have a sharp peak in susceptibility. In length, in correlation length, we don't have similar in another side of pictures. Well, now our conclusion, because this work isn't finished, because this model gives us some surprise. One surprise, one not surprise, because we see in the Mancini work, there is anomalous behavior in one-dimensional extended Hubbard model, one-dimensional model, as soon as model pots. Another interesting thing that Mancini said in your article, that if you define the number operator equal 1 minus spin 1, the Hubbard model is mapped in easy spin 1. The first question, is in spin 1 in one dimension have pseudo transition? The answer is not in this moment. You didn't find pseudo transition in one-dimensional easy model. Probably the pseudo transition in spin 1 in one-dimensional is hiding. Como is hiding in easy spin half. It's necessary more study about this. But there are another questions that important to us. Another question that, in our opinion, is necessary answer that are anomalous behavior in one-dimensional quantum model. We don't know the question. We don't know the answer about this question. Of trying to obtain usando easing with transverse magnetic field, and the answer is not. Pseudo transition is destroyed with quantum systems. But there is one interesting thing that in nanowire, these terms was very important to pseudo transition in one wire. We identify it in nanowire. But in this moment, we can find pseudo transition in spin 1 in one dimension U. But the Mancini said in this article too that we have look this map with we pay attention in this map. Mancini said about it. Pay attention, because here you have potential chemical potential involved in this map. It's important to have more attention with this map to define this relation and defining that pseudo transition there is in one-dimensional easy model with spin 1. Now, it's important to study magnetic caloric effect in this model too. It was one of first objective in this model. Então, it's necessary to study magnetic caloric too in region that anomalous behavior. And another question that I don't write here, what's the consequence of anomalous behavior, or what's the signature of anomalous behavior in two dimension? When if we look the non-wire, we can think about it's possible to come into two dimension using non-wire. There is some signature of the pseudo transition in two dimension. We don't know about this question. We don't know answer about this question. Here we have the reference that I said, that you write. First, our first work about the pseudo transition. Second is work with Oleg that we associated the pseudo transition to effective magnetic field equals. Right? Here you have a work that we studied the exponent criticals. Here we have work about the nanowiring. Here we have the work of the Hubbard model. Thank you for attention.